All right, example 4, constructing a grouped frequency distribution. All right, so we have a test that 40 students took, and these are their scores. If I were to do a frequency distribution table and I looked for the lowest grade and counted up how many had the lowest grade and then how many had the second lowest and how many had the third lowest, um, that wouldn't do much different from what I have here because there's so many different scores, and it's pretty rare for somebody to have the exact 100% exact same score out of 100. So rather than just doing a regular frequency distribution table, it's helpful if we group the data into what are called classes. And it's not um, like a math class. It's not like an English class. It's a different kind of class. We're using the word class differently. So what we do, let's see if I can, yeah. What we're doing is we're going to um, group them into a 10-point range. Letter grades are generally based on a 10-point range. In other words, if you have a score of between 70 and 79, we generally call that a C. So because we group letter grades based on 10 points, that's how we are going to assign our classes. So it's kind of hard to see with this in the way. So what we're going to do is we're going to have a class between 40 and 49. The reason why we choose 40 to 49 as the lowest class, our lowest score does not go below 40. And I believe the lowest score is 43. But that doesn't mean we're going to have our class starting at 43. So we want to make sure each class is the exact same size. So if we have 10 points for this class, then we need 10 points for this class and 10 points for this and 10 points for this and 10 points for that. Does that make sense? All right. So now when we do our frequency distribution, we are going to use 40 to 49. And we are going to count up how many are between 40 and 49. So we've got 1, 2, 3. All right, so I see 3 of them. And so then we would have 50 to 59. And we would do the same thing. So any in the 50s. So we've got 1, 2, 3, 4, 5, 6, etc. All right, so we would finish that out then, and it would look like this. All right, so between 40 and 49, we had 3, 50 to 59, we had 6, another 6, 11, 9, and 5. You do have to check when we have a frequency distribution table to make sure that when we add these up, it equals the 40 that we originally had. So just kind of double check yourself, make sure when we add these up that we didn't miss any of our numbers. The class 40 to 49 has 40 as, this is called the lower class limit. 40 is the lower class limit. 50 would be the lower class limit for this class. 60 would be the lower class limit. The upper class limit for this class would be 49. So this is upper class limit, upper class limit, upper class limit. The width is 10. Occasionally, you know how I said make sure all of the classes are the same width? occasionally, very rarely, we make either the first class or the last class bigger, so that we can take into account, so let's suppose, for example, we had one student that got a 7 on the test. So rather than creating a class between 0 and 9, and then between 10 and 19, and then between 20, when there was only that one student that was way outside of the range of everybody else, we would make maybe this class, but 0 to 49. So this would be a larger class. It doesn't happen very often, but sometimes we do that. Histograms and frequency polygons. A histogram, we take that grouped frequency distribution and we make a bar chart. With a histogram, you have to make sure that the bars are next to each other. Okay. And what else? I can't think of anything else. Okay. Yeah, I can't think of anything else. A frequency polygon is a line graph where we take the frequency distribution. So there was one boy that achieved maximum growth in height at age 10. So we would put a point here. And then there were two boys that achieved maximum yearly growth at age 11. So we would put a point here. Guys, don't draw the histogram. When you're doing this frequency polygon, don't draw the histogram first. Just put a point, just put a point, just put a point, and connect them with lines. Okay? And it's a pet peeve of mine. Don't draw the histogram. Stem and leaf plot, another way of organizing information. The stem, what's called the stem, is the tens digit. The leaf is the units digit. This will make more sense when we do an example. So we have the same information that we had for that stats test. And so what we're going to do, all right, our lowest score, I believe, was in the 40s. So we're going to put a 4 here. This is our tens unit. And we're going to put a 3 here. So our tens unit and our units, our digits. So then our next lowest score, I believe, was 45. So now instead of putting a 4 again and then a 5, I'm just going to put a 5 like that. And then for 47, I am just going to put a 7. Okay. Technically, these do not have to be in order. These do. The tens units do. 5, 6, 7, 8, 9. These don't have to be in order technically, but please do. If you're going to be writing it, please put these in order. It just makes it a whole lot easier for teachers to grade if these are in order, but technically they do not have to be in order. So I have a 50. If I had a duplicate, if I had two 50s, I don't remember if I had a duplicate, but if I had two 50s, I would just put another 0. If I had three 50s, I'd put another 0. So when you have duplicates, you do have to write the duplicates. Okay. So this is what the finished stem and leaf plot would look like. And notice they did not put the leaves in order, but I'm saying please do. Also, they didn't put commas in between the numbers, and I'm going to say please do. It makes it easier to read if it's not typed up. If you're handwriting it, it makes it easier to read if it has commas in between. All right. I forget who, but there was a book that was published quite a few years ago. It's called How to Lie with Statistics. And it's not that people are actually lying, it's that they're misleading. They're being deceptive. So let's take this information right here, talking about the poverty rate 2001 to 2003, 2004, 2005. Okay. If my goal was to show a huge increase in poverty, then I might create a graph that looks like this. So notice I go 0.4% between my vertical hash marks here. So it looks like there's a huge leap when it's 0.4%. On the other hand, if my goal was to say, oh no, US poverty rate, it's not growing very fast at all whatsoever, then I might go label my vertical axis like this with 2 percentage points in between. And this looks like there's hardly any increase in the poverty rate, whereas this one looks like a huge increase, and it's the same exact information. So graphs can be used to distort the data, even if they are actually using legitimate data. This graph over here makes it look like there's a huge increase, and this one makes it look like there's not an increase at all. So the graph on the left stretches the scale on the vertical axis to create an impression of rapidly increasing poverty rate, where the graph on the right compresses the scale to create an impression of a slowly increasing poverty rate. It's the same information, it just is expressed differently. All right. So things you should watch out for when you see a graph. Is there a title that explains what's being displayed? Numbers on the tick marks on the vertical axis to indicate the scale. Has the scale been varied to create a more or less dramatic impression? Do too many design and cosmetic effects draw attention from or distort the data? I'll show you an example of that pretty quickly or soon in a coming up slide. Has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? So let's suppose, for example, I put 1990 here, and then I put 2000. So this is 10 years, but the next interval I put equally spaced, I put 2020. That would distort the data, right? Has a time interval been chosen that allows the data to be interpreted in various ways? Are bar sizes scaled proportionally in terms of the data they represent? Is there a source for the data? Does the data come from an entire population or just a sample? Was a random sample used? And if so, are there possible differences between what is displayed in the graph and what is occurring in the entire population? Who is presenting the visual display? Do they have a special case to make for or against the trend shown by the graph? I remember seeing a table that was talking about how beneficial milk is, to drink. And it was coming from an organization that represents dairy farmers. Well, of course, they have an agenda. They want to make it seem like drinking milk is really, really good for you because they want people to buy milk. So they had a goal. They had a special case. They wanted you to buy the milk. So can you trust the data? Maybe, but you're going to want to check into it a little bit further. You're probably not going to want to take the data, without doing some investigation research on your own. This is the example I was talking about. So we have the number of square feet in an average US single family home. In 1980, it was 1,740. 1990, it was 2,080. And 2010, it was 2,392. Okay. So with the home right here is equal height, but they put different frontal additions on the house and the shadow. It's impossible to tell if it's proportionately depicted. The time intervals on the horizontal axis are not uniform in size. We go a 10-year and then we go a 20-year gap, making it appear, I like this phrase, dwelling swelling, has been linear when in fact it hasn't been linear. It looks like a linear growth, but it isn't linear. There was a greater increase in area from 1980 to 1990, averaging 34 square feet per year. Then there was between 1990 and 2010, which was only averaging 15.6 square feet per year growth. So it makes it look like the growth was at the same rate when in fact it wasn't at all. So yeah, this is very deceptive. And they're trying to make it look like it grew really, really rapidly when in fact the growth actually slowed down quite a bit between 1990 and 2010. All right, there you go.